So in the last video, I thought I finished up this section on polynomials and their different rules, and then I went and started recording videos for the next section and realized that a topic that I thought was in the next section is not. It's in this section. So this might feel a little bit out of place since we already did the applications of what we've learned in this section kind of, but there's a few more derivative rules I got to teach you, and that's what this video is going to be devoted to. So when you get the hang of the power rule and the coefficient rule and the sum and difference rule, you're feeling pretty good about taking derivatives, but there are still functions out there that you can't take derivatives of. What else could we possibly need is kind of what I'm getting at here. And one specific family of functions that we don't yet know how to take derivatives of are exponential functions. So for example, if you had a function like f of x equals 2 to the x power, like you see pictured right here, you might think that you could use the power rule, right? You might think that f prime of x is equal to, it's not, so I'll put a does not equal sign, but you might think that you kind of take this x down in front, I guess, and then leave the 2 alone and then make this x minus 1, right? That kind of makes some sort of sense. Turns out that doesn't work. The power rule only works when the base is the exponent and the exponent is a constant. So if this were x to the second power, absolutely use the power rule, but it's not. It's 2 to the x power, so you can absolutely not use the power rule. And so you might be like, all right, don't tell me what I can't use. Maybe tell me what I can use. And before I kind of give you the punchline, I want to make the point that if you think about what a derivative is, right, the slope of the tangent line, we can kind of sketch a few tangent lines, right? Like here at x equals 0, if I had to sketch a tangent line, it would be what you see pictured in green. And then if we had to ballpark the slope of this line in green, let's say it goes up 1 unit each time it goes over, a little bit more than 1. So it's like some fraction that's a little bit less than 1, right? The slope of this green line. I don't know exactly what it is, but I don't know, maybe like 0.7 or something. Who knows? But then as we go way out here in the tail, I'll try my best to sketch this tangent line here at -4. The slope of this line in green, is damn near horizontal, right? The slope is really, really close to 0. Maybe one more? Maybe at x equals 2, the tangent line would look more or less like this green line, and the slope of this green line, I don't know, it's kind of tough to tell. If I continued the line, maybe it would go through right about here. It looks like it goes up 1, 2, 3 units each time it goes over 1. So what I'm saying is because the slope of the tangent line here is about 3, then f prime of 2, this x coordinate, is give or take 3. And because the slope of this tangent line is a little bit less than 1, I don't know, maybe like 0.8 or something, I could say that f prime of 0, this x coordinate, is about 0.8. And then over here at -4, I would say that f prime of -4 is pretty close to 0. I don't know what it really is. Maybe you'd have to go to the right by 10 units by the time you went up 1 unit. Maybe I'd say that f prime of 4 is about 1/10. The slope of the tangent line gets really close to 0 when I go way to the left on the graph. So if I was trying to sketch the derivative, I'd want it to have a height really close to 0 out here. And then it gets a little bit bigger by the time I get over here to 1. It looks like it has a height of about 0.8, so maybe somewhere in here. And then it continues to get bigger and bigger and bigger as this line gets steeper and steeper. And by the time I get over here to an x coordinate of 2, it's got a height of 3, right? So I got this point at 3, I got this point at 0.8, and then I got this point at maybe 1/10. The point that I'm trying to make is the derivative looks a lot like the original function, right? That's a property of exponential functions. It's not quite there. The derivative isn't exactly the function. It would be really cool if it was, but it's not. But it's at least related. The shape of the derivative is very similar to the shape of the function. We'll return to that later, because I want to introduce one other family. It's not just exponential functions that I want to cover in this video. I also want to cover logarithmic functions. And maybe I can do the same little exercise really quickly. Maybe this time without drawing the actual tangent lines, right? If you think about what the derivative of this function looks like, when I get really close to 0 here, the graph becomes almost vertical, right? It's really, really steep. It's going up really, really steep. So the slope of the tangent line is some large positive number. So the height of the derivative should be some large positive number, way up here somewhere. There's some point somewhere around in here where the slope of the tangent line is 1, where if I were to draw a tangent line, it would be this diagonal line with the slope of 1. So I don't know, somewhere in here, the height should be equal to 1. And the further I go out to the right, the closer this becomes to horizontal. The slope's getting less and less and less the further I go to the right. So the height of the derivative should get closer and closer to 0. What I'm saying is the derivative of this function would, loosely speaking, look like this. It almost looks like the graph in purple here, but reflected vertically, although it turns out that's not the shape that it has. If you're familiar with the graph of y equals 1 over x, it kind of looks like this. It turns out that that's closer to the shape that this thing has. but more on that later. All I wanted to do to introduce these guys is sketch the graph of a function 2 to the x, one specific exponential function, and get an idea about what its derivative looks like. Then take a look at a logarithmic function. This one is log base 2 of x, I probably should have said that. And take a look at its derivative, just to kind of get an idea of what these answers should be. I mean, spoiler alert, eventually I'm going to tell you the rules, right? But I hate the idea of just telling you stuff and being like, trust me, so I want to give a little bit of background. Anyways, without further ado, let's look at some exponential graphs. Here's f of x equals 2 to the x power, the exact same function we looked at above. And then here's its derivative. And note that, just like we drew it up here, it kind of has the same shape, except the derivative is always a little bit less than the height of the function. But look what happens when I switch from 2 to the x power to 3 to the x power. That's the graph shown in red. I can think about the slope of the tangent line to this graph in red at any given point, and I can plot heights according to those slopes. And if I did so, I'd get the derivative. And what the derivative would look like is this thing in blue right here. Again, we kind of have the same shape as we have in red, but this time blue is a little bit bigger than red, whereas this time blue is a little bit less than red. So it's kind of interesting that as I change the base on my exponential function, there's some point at which the derivative sort of passes up the original function. More on that later. Anyways, let me give you the punchline that you've probably been waiting for. The derivative of b to the x power, for any b, it turns out that it's almost just b to the x. You just have to multiply by the natural log of b. And if this weren't a business calculus class, I'd take you through why that has to happen. But it is a business calculus class, so maybe I won't. Maybe I'll just ask you to trust me here. So if you knew this formula and somebody asked you to take the derivative of 2 to the x power, which you see pictured here, you'd be like, that's really easy. It's almost just 2 to the x power, right? It almost just stays alone when I take its derivative. I just have to tack on this constant, this natural log of 2. This is just some number, the natural log of 2. Depending on how much you remember from logs, it's the power that you'd need to raise the number e up to in order to change that into a 2. And it turns out that that power is like 0.7, give or take. So what's going on with this graph in red to produce this graph in blue is I'm just taking the graph in red and I'm multiplying it by that 0.7. When you multiply a function by 0.7, that's a vertical stretch or compression. Because 0.7 is less than 1, it ends up compressing the graph down, and that's why I produce this graph in blue. Similarly, if you need to figure out the derivative of 3 to the x using this rule, you'd be like, well, it's almost just 3 to the x. I just have to multiply that by the natural log of 3. The natural log of 3 is the exponent that you need to raise e up to in order to change that into a 3. But you don't need to worry about all that. The point is just that the natural log of 3 is a little bit more than 1. 1.1, give or take. So to produce the graph in blue, what I do is I start with the graph in red and I just multiply it by 1.1. That's it. When you're taking derivatives of any exponential function, all you got to do is leave the exponential function alone, but remember to tack on the natural log of b. If you remember anything about exponential functions from a pre-calculus class, you may have been told that the number e, that's about 2.71828, it goes on forever. Some people have a lot more digits memorized than I have. Ends up being kind of the perfect base in some sense. Yeah, you can do stuff with a 2 as the base in an exponential function, but it makes a lot more sense to have e as the base. Look what happens when we take the derivative of e to the x. Here's the graph of e to the x right here. If I took the derivative of e to the x using this rule up in red, what I would do is I'd be like, well, you almost leave it alone, but then you have to multiply by this constant, the natural log of e. The natural log of e is defined to be the power that you have to raise e up to change it into e. Well, e is already e, so you just raise it up to the first power. You don't change it at all. What I'm saying is the natural log of e is just equal to 1. So in this formula right here, the derivative of e to the x equals e to the x times 1. In other words, it's just equal to e to the x. And you're like, all right, whatever, who cares? That's actually a really cool result, that the derivative of e to the x is just e to the x. Think about what that's saying. If I were to sketch the derivative of this function, f of x equals e to the x, it would land right on top of this red line. It would be identical. Think about what that's saying. The derivative is the rate of change of something. So the rate of change of this function at any point is just equal to the height of the function at that point. How quickly is this function changing at, I don't know, 1 right here? What is the slope of this line pictured in green? Well, it's just equal to the height of the function, this value right here. We haven't done a whole lot of applications yet, but think about what that implies. If you're trying to model something and the rate at which that thing changes depends upon how much of that thing you have. So think like, I don't know, mold on a piece of bread or something. or the population of some invasive insect in a forest. I don't know. The rate at which those things change is dependent upon how much of it there is, right? If you have a tiny little spot of mold and then you wait an hour, there's not a whole lot more. But if you have a pretty decent amount of mold and then you wait an hour, there's a whole lot more. Same idea with some bugs in a forest, right? If there's just a few of them, it's not a big deal. But if there's a lot of them, the problem is not just that there's a lot of them, but that the amount it's growing by is really large. The fact that the derivative of e to the x is just e to the x not only makes the algebra work out really nice in calculus, but it also makes this function really useful for modeling, as we'll see later on in our class. But really, the big takeaway for this video is just, if you ever take the derivative of an exponential function, now you can do it. If I ask you the derivative of 2 to the x, you know the answer. It's 2 to the x times the natural log of 2. And remember, the natural log of 2 is just some number. Treat it as though it's a constant. And a cool result of that formula is that the derivative of e to the x is just e to the x. To make sure that all makes sense, think about if you could evaluate these two derivatives. Two different questions here. I didn't put them on two different lines because I was short on room. Let's first figure out the derivative of 3 e to the x plus 1. Not a bad idea to stop the video here and make sure that you can do this on your own. What I would do is first recognize that we have two different terms here, right? The 3 e to the x term and the 1. And when I'm taking the derivative of a sum of terms, I can just take the sum of those two individual derivatives. So I get the derivative of 3 e to the x plus the derivative of 1. The derivative of 3 e to the x, this 3 is just a constant, so I can treat it like a constant. I can pull it out in front of my derivative sign. I have 3 times the derivative of e to the x plus the derivative of 1. Now I can use some of my rules. The derivative of e to the x is just e to the x. The derivative of 1 is just 0. So the derivative of 3 e to the x plus 1 is just equal to 3 e to the x. Much like with polynomials, you'll quickly get to the point where you can look at this and immediately give me this answer, and that'll be great. But the first few times through, I'm going to show you all the steps to really show you why things work, because the danger of calculus is using rules where they don't apply. So you have to be more careful than you'd think. Maybe not right now, but soon. What about the derivative of 2 minus 5 to the x power? Well, again, I have two terms. I got the 2. So I'll take the derivative of 2, and then I'll subtract the derivative of the other term, 5 to the x power. The derivative of 2, that's really easy. 2 is a constant, so that's just equal to 0. The derivative of 5 to the x power is almost just 5 to the x power. I got to remember to tack on this natural log of 5. So my answer is negative 5 to the x natural log of 5. If that all makes sense, you picked up everything I need for exponential functions. So now let me do kind of something similar for logarithmic functions. Remember earlier we looked at the graph of g of x equals log base 2 of x, and I kind of tried to sketch its derivative. Turns out the derivative looks like what's pictured in orange. And the equation of that thing that's pictured in orange, I can get from this rule up here. It says the derivative of log base b for any b of x is almost 1 over x. It's just you got to remember to tack on this natural log of whatever the base is down here in the denominator. Kind of like the rule up here where we got to make sure we tack on the natural log of the base. But when you're dealing with exponential functions, you just multiply it by that natural log of the base. When you're dealing with logarithmic functions, that natural log of the base ends up down in the denominator. So if my function is log base 2 of x, my derivative is 1 divided by x times the natural log of 2. That's what you see pictured in orange here. Again, the case where the base is equal to e is really interesting, right? If we're taking the derivative of the natural log of x, this is the log base e of x, then what we would do using this rule is we'd have 1 divided by x times the natural log of that base, e. But again, as we talked about above, the natural log of e is just equal to 1. So we'd have 1 divided by x times 1, or just 1 divided by x. The derivative of the natural log of x is just 1 over x. Here's the graph of 1 over x and the graph of the natural log of x. So you can kind of see that result. This is kind of the general case that will work for any base log, but natural logs are going to end up being really useful in our class for the same reason that using an e as the base is really useful in our class. So you're often going to run into the natural log of x. And rather than think about it as a special case of this rule, you could, if you want, just memorize that the derivative of natural log of x is just 1 over x. Is that all sinking in? Maybe I can leave you with one question to test your knowledge. What if you were asked to find the derivative of this big mess right here? If you can figure this out, you got everything you need for logs. But be careful, there's a couple little tricks in here. I would start by recognizing that we have 3 different terms here. So let's take the derivative of each term individually. For the first term, you might notice that we have this constant of 3. And so maybe you remember that we can take constants and pull them out in front. Don't forget to apply your old rules, even though we're learning new rules. We'd have 3 times the derivative of the log base 2 of x. Same idea here. We can pull this 5 out in front, and we got negative 5 times the derivative of the natural log of x. And then this term over here, I'm going to save that for a minute. I'm not going to do anything right now because there's nothing that I can pull out in front. This is going to end up being the tricky part of this problem. Over here, I got 3 times the derivative of the log base 2 of x. So if you use this formula up here, you know that the log base 2 of x is 1 divided by x times the natural log of 2. So I get 3 times 1 divided by x times the natural log of 2. From this term, I still got the negative 5, and then I got to multiply that by the derivative of the natural log of x. And the derivative of natural log of x, because natural log is log base e, is 1 divided by x times the natural log of e, or just 1 divided by x. And then you get over here to this term, the derivative of log of 100. First of all, you're like, ooh, you're trying to trick me here. You didn't write the base, but I remember when I learned about logs that if you don't write the base, it's implied that the base is 10. And yes, that's very good. And then you're like, okay, so I do some sort of like 1 over x times the natural log of 10 or something? No. The reason why is this is not a function. This is a constant. The log of 100 is a number. Turns out it's the number 2, but you don't have to know that. This is just some number. If I'm taking the derivative of a number that doesn't have any variables associated with it at all, the answer for that derivative is just 0. Almost everyone gets that wrong the first time. You think that you should do some 1 over x something or other, but you don't because there's no x's in here. The derivative of any constant is just 0. So this is my final answer. I could clean this up a little bit by thinking about this 3 as 3 over 1 and then multiplying these fractions to get 3 divided by x times the natural log of 2. And similarly, I could think about this 5 as 5 over 1 and multiplying these fractions to get 5 over x. I think this is how I would write the derivative, but really it's just a simplification of the line that you see right here. For real this time, we're done with this section.